right. Good morning, everyone. Thanks, Michael, for inviting me. Really excited to be here. So today I'm going to talk to you about our studies of how programmers interact with AI programming assistants. So, and this is joint work with my wonderful students, Shraddha, Kasra, and Lisa, and Michael, and with Soren Lerner, who is also at UC San Diego. So as you all probably know, the AI programming assistants are sort of taking the world of programming by storm, changing the way we program, and of course, new programming assistants are sort of emerging all the time. And so now is a perfect time to ask some questions about how these tools are supposed to work, right? So how they're supposed to be designed. And we should start with kind of sort of just exploring how programmers are even using those tools, right? So what do programmers use them for? How do programmers express their intent to those tools of what they want to achieve, right? Oops, that's not good. What are your questions about your favorite programming assistant? What do you want to know about them? What do you think is important to ask? So I said two things. What do programmers use them for, and how do they express their intent? What other important questions do you think we should be asking?
What modes could exist for the assistants that don't currently?
Modes as in interaction modes, right? So yeah, exactly. So we have assistants like ChatGPT that has like a chat mode, and we have something like Copilot that is more of an autocomplete thing, right? So what other interaction models could we have, right? Anything else that comes to mind? Sure.
Maybe how they compare to like, there are things that are things we like them, like pair programming, or maybe like just like searching something on the web. Like how does
So how do the neural assistants compare with other techniques for improving programming, like other kinds of assistants, right? So either human or existing tools. Sure, that's an awesome one. Anyone else? Oh, we have the video. Okay, great. So things that came to our mind is, so when an AI assistant suggests some code, how do programmers validate it? And by validate, I mean like, how do they determine if that's the code that they actually want, right? And if they do determine that there's some errors in this code, how do they cope with it? Do they just throw it out and write the code themselves, or they try to fix it, stuff like that? Okay, and so in this talk, I will tell you about two pieces of work that our group did. The first one is a grounded theory study of AI-assisted programming, so in particular programming with Copilot, and I will tell you in a second what it means to be a grounded theory study. And this work is called Grounded Copilot, and it is to appear in ASA'23. And the second piece of work that was sort of inspired by the lessons that we learned from the first study is called LEAP, and so this is a new design that we came up with that helps programmers validate AI-generated code, and it is currently under review. Okay, so let's first focus on the Grounded Copilot. This part of the talk will be in three parts. So first, tell you about the grounded theory method. Then I'll tell you about the theory that we came up with and the recommendations for future tools that are based on this theory. Okay, so what is this grounded theory that I keep talking about? So usually when we do human experiments, it is to test some hypothesis, right? So we want to know if something is true, and we do an experiment and check it. But sometimes we don't have a hypothesis. We don't even know what's going on in the first place, right? So this is where grounded theory comes in. So it's a methodology that comes from social sciences, but it's slowly kind of finding its way into software engineering and programming languages. The idea of grounded theory is that you don't have any a priori hypothesis. You're trying to build up a theory from data, from the ground up, right? And so the way you do your study sort of in this circular fashion, you first collect some data, then you try to interpret this data, then you build a theory based on that interpretation, and then if there's still some unknowns in your theory, you just keep doing that. You just keep collecting data, okay, and refining your theory. So what did it mean in our case? So our data collection phase was basically a bunch of programming sessions. So we set some programmers in front of an IDE with Copilot, and we asked them to solve some programming tasks, and then we performed interviews, right? So our data interpretation was something that's called qualitative coding. So for those of you who haven't heard about this before, qualitative coding means when you analyze a bunch of data. In our case, this was the videos of the sessions, right, and also the interviews, and you kind of tag all the events that are happening in this data, and you're trying to categorize them, right? And usually several people are doing this tagging and then trying to make the tags converge, right? And this is how you make sense of what's happening in this data. Okay, so first we had to give those programmers some tasks to solve. The first two tasks that we developed for them were chat server and chat client. So our goal in developing those original tasks is we wanted to have something that's not just like a standalone, like one kind of function, which is what many of the previous studies did in this area. We wanted to have something that's kind of in the context of an existing code base, even though the code base was not very large, but we kind of developed this secure chat server client, and then we asked the programmers to add some functionality to it, basically to implement some functionality. And so the chat server was more focusing on implementing the business logic of the chat. Sort of, if I get this message, what should I do, right? If I get this command, what should I do? And then the chat client was more focusing on implementing the networking code, and we also gave them a custom crypto API just to test what happens if Copilot has to use the library that it has not seen before. And we had two languages that the participants could choose, either Python or Rust. And then during the study, we kind of added more tasks just to test particular aspects of the theory. One was a Benford's law task, which doesn't really matter what it means, but it included a familiar algorithm part and then another part that had to use the matplotlib library, and it also used two languages within the same task, Rust and Python. And then finally, we added a little string rewriting task where the point was that it was very easy to test. So for this study, we recruited 20 participants from various places and with a range of language proficiency and Copilot experience. Okay, so what did we find? Our main finding was that programmers' interaction with Copilot is bimodal. So maybe you have heard of thinking fast and slow, right? So we kind of compare it with programming fast and slow, right? What do I mean by that? So we can sort of roughly split all the interactions between programmers and Copilot into two modes, which we call acceleration mode and exploration mode. So very briefly, acceleration mode is when the programmer uses Copilot as sort of an advanced autocomplete, right? So this happens when the programmer already has a plan of what they want to implement, and Copilot just helps them get there faster. Whereas exploration mode is you can think of the programmer is using the assistant as an advanced Stack Overflow. This happens when the programmer has no idea how to implement what they want, right? And they use Copilot to drive this process and to suggest potential solutions. Okay, so let me talk a little bit, give me an example, let me give you an example of each one of those modes, starting with acceleration. So this is a snippet from one of our tasks where the goal was to do some kind of string transformations. And what happened was the programmer was able to break down this task into sort of micro tasks where they had a very good idea of how to solve each individual micro task. So this in particular was the micro task of, okay, first I need to parse the input file, right, into some kind of dictionary. And so then the programmer is just typing away. They're not explicitly prompting Copilot, but they just pause at some point. And then Copilot auto-completed this to the end of line, right? Then what was the programmer's reaction? The programmer barely even paused to analyze it. They clearly just kind of intuitively pattern matched in their head and decided, oh, this looks very much like I wanted to write, like something I wanted to write anyway, right? So they very quickly accepted it without leaving their state of flow, right? This is what kind of a typical acceleration interaction could look like. And so here I have a video. Oh, I didn't plug this in. But you said that it might work with HDMI. Okay, so let's just, so this is a video from one of our sessions that is illustrating an interaction in acceleration mode. No, there's no, wait. There is no sound. Oh, it does say HDMI to HDMI output. I can, huh? Maybe I can change the output to speakers and then just use this. I don't know if that will work or not. Sorry for the technical difficulties.
Oh, no, this is values. Username equals text. Then, oh, there you go. Username already taken.
Yeah, so this was an example of how the programmer just saw exactly what they wanted, and they kind of very quickly accepted it by sort of intuitive pattern matching. Okay, now an example of a typical interaction in exploration mode. So this is the programmer is trying to plot a histogram in matplotlib. They are not familiar with matplotlib at all, right? So they have no idea of how to do this. So in this case, the programmer intentionally prompts Copilot with a comment. So you might not be able to see the comment, but it says, plot the first digits of the Fibonacci sequence as a histogram. And then the programmer explicitly invokes the Copilot side panel. In case you don't know what it is the side panel where Copilot can suggest multiple alternative suggestions. Then the programmer explores those or examines those suggestions carefully and compares different suggestions between each other. So one behavior that we observed a lot is that programmers would, so especially in these kind of API-heavy tasks, they would compare what API calls Copilot performs across the different solutions. And if some call appears a lot, they would think, oh, it must be that the tool is very confident that this is the right call to make, in which, so in this case, it would be the PLT hist. Happens to be the right thing to do, actually. So then the programmer might pick one of those suggestions, or what we actually also observed a lot is they might cherry pick different parts from the different suggestions, and they would be, then they will proceed to explicitly validate the code, for example, by running it on some examples or by consulting documentation, right? And if they see some behavior that they did not expect, they would actually be willing to edit and debug the code, right? Because that is still is perceived as the most convenient alternative for them, because otherwise they don't know how to write the code otherwise. So here is an example of an exploration interaction.
Where I say, oh, wow, actually, look at that. Wow. I wonder if this is from the solution or something. Okay, come on. Try, sure. Okay, not handshake, I like that. Okay. This seems potentially wrong, but I'll keep going in. Sure. Great. Wow, I'm such a good coder.
So this was obviously a little bit tongue-in-cheek, but you know, this is one example of what such an interaction could look like. So that particular one didn't invoke the multiple suggestion panel, but this is also what something we saw a lot. So if we look at the prevalence of the different modes in how programmers use them, so we found that if you just look at the time that the programmers spent in each mode, it's dominated by exploration mode, but this is basically because each exploration interaction just takes much longer, right? But interestingly, if you split those by the programmer's expertise in a language, then you can see that programmers that are very proficient in the language, they tend to accelerate more and explore less, which makes sense, right? Because they already know what to do in that language. There was also a difference if you split them by prior Copilot usage. So on the left, you see people who have used Copilot before, so you can see that they accelerate more than the people who have not used it before. And so we attribute this to actually people who have not used Copilot before, they have more trust that the tool can help them with more complex tasks, and so they attempt that more, right? Whereas people who have used it before, they have like a much more realistic expectations of what it can or cannot do, so they start using it more for acceleration and less for exploration. So just to sum up sort of the difference between the two modes, So how do different behaviors differ in the two modes, right? So if you look at prompting, in acceleration mode, it's more unintentional, just pausing, right, during typing, whereas in exploration mode, programmers would intentionally prompt Copilot with natural language comments or invoking the side panel. If you look at validation behavior, in acceleration mode is sort of this subconscious kind of pattern matching validation, whereas in exploration, they would do it explicitly by executing the code or examining it very carefully, or consulting documentation. So with respect to the scope of a suggestion that the programmers expect, in acceleration mode, programmers really want suggestions that only span until the end of their current unit of focus. So in an imperative language, that's usually the current statement, so they want suggestions till the end of the line. What was interesting is in functional languages like Haskell, programmers expect suggestions that are even shorter, because often in a single line you're composing multiple functions, and that's already too much if it suggests like the whole line, right? So you want the next function composition. Whereas in exploration mode, programmers are perfectly willing to examine like an entire function, right? Or even multiple alternatives. And finally, their tolerance to the suggestion mismatching their expectation. In acceleration mode, basically no tolerance, right? So either they see that the suggestion matches the expectation exactly and they accept it. If it doesn't look like something they expected, they would just reject it immediately, right? Whereas in exploration mode, they're willing to edit it, to debug it, or to rip apart the solution and cherry pick from it, stuff like that. Okay, so based on these observations, what kind of recommendation can you make for a future AI assistance? Well, first you need to look at the main challenges that we observed, and the important thing is that these main challenges are really different in two different modes, right? So actually what we found the most challenging to participants in acceleration mode is that when Copilot gives long and unexpected suggestions, they break programmer's flow and distract the programmer, right? So, and this was the main problem in this mode. Here's an example of that.
Want to do? What do you want? That's interesting. Okay, hang on. So. See, I don't know why. I was about to write the code. I was about to write the code and I knew what I wanted to write, but now I'm sitting here seeing if this somehow had come up with something better than the person who's been writing Haskell for 5 years. Why am I doing that? Why am I giving it the time of day? But no, this is not what I want. Okay.
So, and we found that these distractions were actually the main reason that participants who have used Copilot before have disabled it, right, and weren't using the tool at all. Whereas in exploration mode, the main challenges sort of had to do with validating and debugging long suggestions, and also participants did want to see multiple suggestions, but they found them hard to distinguish just with that multi-suggestion pane that Copilot offers. So based on that, our main recommendation actually is that future tools should be aware of these modes and maybe design different interventions based on which mode that they're targeting. Secondly, we thought of different things that can be improved, specifically in exploration mode. So we wanted to think about how can we help programmers simplify this validation process and maybe better support for comparing alternative suggestions. So this actually brings me to the second part of my talk, but I need to know how much time I have because we started late. And okay, awesome. Okay, great. That's perfect. Okay, so so these, in particular, these two recommendations for how to improve the exploration mode led us to this other work that we did that is called LEAP. We're trying to help programmers validate AI-generated code. So LEAP stands for Live Exploration of AI-Generated Programs. And so why is it called live exploration? Well, it's because our idea is to use live programming to help programmers with that exploration task, specifically the validation aspect of it. So what is live programming? Can you raise your hand if you know what live programming is? Okay, so some people do. But so basically what we understand by live programming is the continuous display of runtime values of a program, right? That's basically showing you what's going on as you type, okay? That's the idea. So in this part of the talk, I will start with a demo of LEAP, and then tell you about the study that we did and the findings from that study. Okay, so let's see if this works. And this is courtesy of Khasra, who's sitting right there. I don't know if you can see anything, guys. Okay, so this is our LEAP IDE. So this is just, you know, looks like a regular Python editor, except something weird that you see are these boxes that appear on the right of each line of code. And so these boxes are basically showing the runtime values. So in this case, for any variable that's assigned in this line, right? So you can see, for example, or printed on this line, right? So for example, it's showing us the value of this list data. Of course, this is not super impressive because we just assigned a constant to it. But for example, the main thing is that these boxes that are called projection boxes, they will update as I type. So for example, if I say, if I want to get the length of data, right, then it will immediately show me that the length is 5, right? Okay, so but in LEAP, not only can you write the code yourself and see what it's doing, but you can also invoke a programmer's assistant. And so let's do that. Let's say I want to compute the mean of this list. Compute mean of data, right? So I can just write a natural language prompt and then invoke the assistant. I should probably make this smaller because otherwise it's just, oops. Okay. Interesting. My first suggestion is a comment to create the bar chart. But the second suggestion, well, so this is different every time. I have no control over this, so this is querying an OpenAI. So let's say I have no idea what mean is. The main idea in LEAP is that you can preview each one of those suggestions, right, and use live programming to see what's happening. So in this one, mean is 0, which doesn't sound right to me, right? But if I look at this previous one, this sounds more reasonable, so I can just accept this. Let's try something a little bit more interesting. Maybe I want to compute the mode of data. Let's see what it comes up with this time. The first one, and I kind of know that the mode is what? What is the mode of this? 3, exactly. But if I look here, this is returning 5, which is not correct. Let me try this other suggestion. So for the first one, you might say, okay, from the code, I already see that it's incorrect, right? But for the second one, maybe I don't know what it means. Key equals data.count, who knows? But with leap, I immediately see that it returns the right thing. And given the fact that the code kind of makes sense. So this is how I can validate it and say, yeah, this is probably what I want. Just the last example, so something a little bit more fun. Let's plot our data, right? So for example, I can ask, create a bar chart of data. Let's see what it's suggesting. Okay, not many differences, unfortunately, but you can see that Leap can also show you the charts. It doesn't look as good when it's so zoomed in. You don't see that. So do we have any other suggestions? No, unfortunately, they're all the same this time. But okay, we can accept this and maybe do something more interesting, like make all bars different color. Can you do that? That doesn't sound like that will help. But let's see, maybe this one. Yay, we achieved what we wanted. Okay, it's very, okay, let me zoom out a little bit just so that you can see it. Okay, so, and now this looks like what I want, so I will accept the suggestion. Cool? Okay. Let's go back to the slides. So this is what Leap looks like. So it helps you validate AI suggestions by giving you live programming so that you can see all the runtime values immediately. And you can compare the different suggestions. You can preview different suggestions that you get from the model. Okay, so we did this user study where we compared two experimental conditions. The no PB, so no projection boxes, condition was we had the same editor with the same AI assistant, but there were no projection boxes. If you want to run the program, you have to use the terminal. And the treatment condition was PB, which means what I just showed you, right? AI assistant plus projection boxes. Okay, so what did we want to figure out? We wanted to figure out how live programming affects the correctness of the code. So if we ask the programmers to solve a task, would they solve it more correctly with or without projection boxes? How does it affect over and under reliance on AI? So by under reliance, we mean lack of trust in AI suggestions, and by over reliance, we mean you accept something that is incorrect. And finally, cognitive load of using the AI assistants. So for this study, we also designed a couple of different tasks. So one task had to do with cleaning some data using pandas. Another one was an algorithmic task finding the most frequent bigram in a string. There was a box plot task where you had to use matplotlib to make some complicated plot. And there was a string rewriting task, which was actually the same string rewriting task I showed you in the previous study. The main point is that those studies kind of exercise different things, right? The ones on the left are more API heavy, whereas the ones on the right are more algorithmic. Another kind of design decision in our study is we had kind of two modes in which we asked participants to use our tool. For the first two tasks, we used what we call the fixed prompt mode, which basically means that we already fixed both the prompt and the suggestions that they're getting, and we just asked them to pick the suggestions they think is correct, and if nothing is correct, pick one and edit it, right? So until it's correct. And so we did this just so that we kind of make a controlled kind of experiment where we're not dependent on the randomness of the model. And then for the second part of the study, we just let them use the tool however they wanted, right? But from the second part, we could only extract qualitative findings because it's very random, so it was very hard to get any quantitative data. And finally, another difference was that among the two fixed prompt tasks, we picked the suggestions in such a way that for one of them, multiple suggestions were correct, whereas in the bigrams, no suggestions were absolutely correct. They had to edit the code to get it to be correct. Okay, so for this study, we recruited 17 participants from academia and industry with different Python experience. And so let's see what we found. So if we look at how projection boxes influence correctness, you can see that it's very different depending on, it's sort of different depending on the task, right? So if you remember, in the bigrams task, we had no correct suggestions, right? Whereas in the pandas task, multiple suggestions were correct. So now if you look at, so the projection boxes condition is on top and no projection boxes is on the bottom. So if you look at the pandas task, right, where they only had to pick a correct suggestion, right? Clearly, projection boxes help them do that. Everyone picked correct code, right? Whereas without projection boxes, some people picked something else, right? Whereas if you look at the bigram task, where there was no correct suggestion, you can see an interesting. Sorry, this one was they timed out, so they didn't actually finish. So we gave them 10 minutes to finish the task, right? And if by the end of the task they say, well, I'm still not sure that this is, that I actually completed the task, that would be a timeout, right? So if you look at the bigram task, we see an interesting thing. So projection boxes by themselves didn't really help everyone complete the task correctly, right? Because some of those participants still timed out, but we see that there are no incorrect solutions, right? Whereas in the no PB condition, there were 3 incorrect solutions, which means the participants thought they finished and they thought it was correct, but in fact it was not, right? So as we can see, LEAP helps programmers validate suggestions. In particular, it helps prevent participants from coming up with incorrect code, right? However, it does not by itself help them fix a solution, a suggestion, if there are no correct suggestions available. So this brings us to the second research question about the over and under reliance on the model, which we thought was very interesting. So among all those, so between all those experiments, there were only 6 participants that misjudged correctness of their solution. So either they thought the solution was correct, but it actually wasn't, or the other way around. And all 6 of these participants were in the no PB condition. So there were no PB participants that misjudged the correctness, right? So this leads us to conclude that LEAP reduces both over and under reliance on AI assistants, and our theory is that this happens because it lowers the cost of validation by execution, right? So because you can think of validation as sort of a cost-benefit kind of analysis, right? So if you lower the cost of validation, the programmers, of course, will be doing it more, and they will be getting the code more correct. And this is corroborated by participants' quotes. So for example, participant 3 said, "It was easy to understand the behavior of a code suggestion because the little boxes on the side allowed for you to preview the results." So they actually attributed this to projection boxes. And P1 explicitly put it in terms of cost reduction. They said, "It saved me the effort of writing multiple print statements." Then finally, we also looked at the cognitive load of using the AI assistant. So we used the NASA TLX cognitive load metrics. And so this is showing the results for the pandas task. So remember, the pandas task was it's sort of more API heavy, right, and less algorithmic. And so on this task, it is we actually got a statistically significant difference in cognitive load reduction for all of those metrics except one, I think, hurry. So for this kind of task, like pandas, that was sort of more API heavy and more kind of a one-off task, which makes it very amenable to validation by execution, we find that Leap significantly reduces cognitive load of exploring AI suggestions. And this is basically what I wanted to tell you today about these two studies, and I'm happy to take questions.
Thanks for a really nice talk. We have time for some questions.
Hi, thank you. Very interesting talk. I wonder about the Leap work, if you consider just showing the developers results of testing. Like we ran this code and like bad, good, or 5 tests like you will have in a normal development environment, and how it would affect everything.
Yeah, this is a really good question. So I think if the tests are there, this is a really good idea to show that as well. So one thing where live programming differs from simply running the code and showing the final result is that it actually shows you the execution step by step. And we found that it was important, especially for those like more algorithmic tasks. So participants said that it was really helpful that they could see the results step by step, because otherwise they had to do like mental math going through the code line by line.
Hi. I found the Leap interface very interesting, and I must confess I came in a little late, so if it was already covered, I'm sorry. I use notebooks for doing data exploration, and it has for me, the nice appeal of having it in like one place, so I can do it on small monitors, big monitors, whereas this is on the side. And it's not perfect. It only displays the last value. There are a few problems, whereas you display every value, which is nice. But it's universal, right? Like Visual Studio has their own notebooks. Google Colab has notebooks. Jupyter has notebooks. What is the relative merit of the IDE, you think, of the Leap one?
Yeah, this is a great question. This is something that the reviewers asked us also. Yeah, so the thing that I said about the step-by-step is, I think, one of the big differences, right? So even in a notebook, you see the final result of the execution of a cell, right? So if there is something like algorithmic going on, in like, for example, you have a loop, you don't see like, oh, what happens after each loop iteration, right? So I mean, definitely. So I think that the results of our study also can be applied somewhat to notebooks, right? So I think the benefits of this liveness, right, that we find, some of them apply also to notebooks, right? So, but this is slightly different, and it can be so I think it can be applied to different kinds of problems than notebooks can, right? So like if you have these more algorithmic problems, then live programming would be more useful. But also there's this other aspect of Leap where you can preview multiple solutions, right? And so if you were to integrate this into a notebook environment, you would still need that part, right? Because the idea here would be that you can go between solutions, right, and keep previewing different ones until you pick one, right? So that kind of functionality can also be integrated into notebooks, but you would have to implement that as well, right? Well, then you would have to go in, copy-paste the thing from the panel, right? Insert it manually into the cell, run it, right? So this is, our study shows that this is really about lowering the cost, right? So like if you need to do even like 3 extra clicks to copy paste and to run, right? So this is just this little thing that would nudge the programmer to not do it, to not do the validation, right?
Hi, Jose Renal. In programming, before AI, there is the test-driven development, and there is some pros and cons. I wonder what is your thoughts, because my feeling is that having AI is going to push the balance go more towards test-driven development. It has more advantages going there when you have AI. Because you develop the test, you have small functions, you can build it, maybe the AI builds it there. So it changes the way that you program, not so much that it complements the functions like Copilot. I still think there is a lot of issues with the current AIs that we're using. The HCI part of the AI is what I find issues.
Yeah,
I'm just sure what's your thoughts?
I think this is a really good point. I think both AI assistants and sort of this live programming environments, they sort of make writing tests more worthwhile, right? So in that sense, it's great.
Hi, nice talk. I was just wondering if qualitatively you had any kind of sense of what kind of mistakes Copilot seems to make when you ask it to write code, and what the errors kind of look like.
Yeah, so this question is kind of hard to answer just because it changes so much over time. I mean, I do use Copilot, and I found that it got much better in the last maybe half a year. Yeah, and it also depends on the task a lot. So, yeah, I think it's hard to say.
Hi, I love the talk.
Thank
It would seem like these two different parts have almost like conflicting resolutions, right? Like in the first one, the grounded Copilot, kind of the conclusion, at least the takeaway that I had, is that these multi-line suggestions are not super useful, and this exploration mode for more experienced developers is kind of like pushed aside. And then in the Leap demo, kind of like exploration mode is the thing that you're doing, right? Like you're writing a comment and then you're asking for some suggestion. And then I guess the takeaway and the thing that unites them is that you've said that the key to Leap is that you're lowering this like cost of validation. And I wonder if you've done any research into lowering the cost of validation for experienced programmers inside of Copilot.
This is a great question. So I think you're right that when we were looking at the Copilot, we find that the more experience you have, the less you use exploration mode, right? And the more you just try to stay in exploration mode. But I think, well, at least one of the explanations for that is that the exploration mode in Copilot is just so poorly designed that people just stop using it, right? So you're staring at, 10 programs that you can't see the differences between them, right? So like it's hard to figure out their behavior. So one way to approach this is to say, well, let's just abandon exploration and just use AI assistants for exploration, right? But we thought we'd go a different way, and we're like, well, if we improve exploration, right? So if we make the affordances better for exploration, then maybe programmers will start using it, right? And so Leap was one of our ideas for how to do that. We're working on some other ones. So for example, my student Michael is currently working on this idea for like how to present a lot of different suggestions, maybe 100 suggestions to a programmer, but not in a linear fashion that they have to read 100 different programs, but sort of to structure them and organize them in a way that you can drill down and quickly find something that you need, right? So basically, I think the answer to your question is I don't think we should give up on exploration, because I think it's a thing that people want to do. We just don't have good tools for it.